Welcome. Today, we'll be discussing special right triangles. Now, those triangles whose interior angles are 45, 45, and 90 degrees, we call that a special right triangle. And also, if the interior angle of a triangle has measurements of 60, 30, 90, we call it a special right triangle. So we're going to take in consideration these two special right triangles throughout the lesson. All right, so let's take a look at the following introduction question. Let's just recap of what we have been discussing so far. Can we use the Pythagorean theorem to find the length of the missing side? Yeah, definitely, because as long as you do have a right triangle, if you know two sides, then you can definitely find the value of the third, which in this case, if we set it up properly, it will become 2 squared plus 2 squared, that's equal to c squared, where c is the hypotenuse, which we don't know. So now this becomes 4 plus 4, c squared, so 8 is c squared. So c is the square root of 8, which recall that we can simplify this, because now 8, we can simplify it at a times 2, where c, square root of 4 is 2, so now this can just be simplified as 2 square roots of 2. So just, we're just reviewing our Pythagorean theorem before we actually use it throughout the lesson. So now, for example, B, notice that what we're missing is one of the legs. We have one leg, we have the hypotenuse, so we can definitely use the Pythagorean theorem to solve the third side because we know that it's a right triangle. So if we set this properly, it will become 2 squared plus, we don't know this length, so let's call it B. So B squared equals 4 squared. So let's simplify it. 2 to the second, that's 4. B squared, 16. It would take away 4 to both sides. So now this becomes B squared, and that becomes 12. So B is the square root of 12. Notice that we can still simplify the square root of 12 because 12 can be seen as 4 times 3. And we know what the square root of 4 is. So now this becomes B is just 2 square roots of 3. Okay, so this introduction question was just for you to recall how can we use the Pythagorean theorem to solve for the missing side. Now, let's have the following discussion. So now, this is the first special right triangle. It is a triangle whose interior angles are 45, 45, and 90. And given the following right triangle, can we find an expression for all the sides of the triangle? Which notice that at least in this special right triangle, we have not placed a value for any of the sides. All we know is that the side that we do have here, we're just going to call it x. But what do we know about this triangle? Boy, this is 45 and this is 45. Then I can see this as an isosceles right triangle. So therefore, if this side has a measure of x, then therefore this side must have the same measure of x because we have an isosceles right triangle. This is 45, so 5 must be the same length. So how does this help us? Well, if I know that this side is x, and I know that this side is x as well, and that's a right triangle, so therefore I can use the Pythagorean theorem, which is going to be this side square plus this side square equals, let's call the hypotenuse c. So if we simplify this, x squared plus x squared, that's 2x squares equals c squared. Let's solve for c. If we want to solve for c, this is equivalent to just taking the square root. So now I know that c is equal to the square root of 2x squared, which again, this can be simplified as just the square root of 2 times the square root of x squared. But in this case, the square root cancels out with this 2. So now we know that the hypotenuse is equivalent to the square root of 2 times x. And keep this expression in mind. Because what this is saying is the following. In any 45, 45, 90 degree angle, triangle, the hypotenuse will always be equivalent to the square root of 2 times the side of any triangle. or one of the legs, I shouldn't call it the side, of the legs of this right triangle. So if you know the length, I'm sorry, if we take a look at a 45, 45, 90-degree triangle, if you know the length of one of the sides on this triangle, to find the hypotenuse, we just gotta get this side and multiply it by the square root of 2, because we just showed that this is true. So keep this very important expression here. What this is saying is that the hypotenuse is equal to the square root of 2 times one of the sides. I shouldn't call it sides. Square root of 2 times the leg. I guess singular is fine. Is square root of 2 times the leg. Oh, let me just rewrite it because I don't like the way that it looks. The hypotenuse will always be equivalent to just the square root of 2 times the leg of the leg of that 45, 45, 90-degree triangles. That will always be the case. And again, this is only true if we have a 45, 45, 90-degree triangle. So keep this expression in mind. So now we can kind of verbalize this. What is the relationship between the legs of the triangle and the hypotenuse? Well, the hypotenuse is always equivalent to the leg of the triangle times the square root of 2. So this is true for a 45, 45, 90-degree triangle. But let's take a look at this second special right triangle, where the second special right triangle, it deals with a 30, 60, 90-degree triangle. But in order for us to have a discussion, let's follow these steps, because these steps these steps are going to reveal a very important property about these special right triangles. So first, notice that the special right triangle has a 30, 60, 30, 60, 90. So our first step is that we want to reflect this triangle over the line AC. So here we have AC. Imagine that you get this triangle and you just reflect it over the line segment AC. So therefore, now this is going to be the image of the reflection. This is B. Let me call this point B prime. And what do I know about this? And again, I guess you can see that it's not drawn to scale, but hopefully you do get the idea here. But what do we know about this so-called reflection or image? Well, if this is reflected, notice that this is 30 degrees, and if I reflect it, this is also 30 degrees. And if this is 60 degrees after the reflection, then this must be 60 degrees as well. Now, what's the relationship between triangle ABC and AB prime C? But the relationship is that they must be congruent angles. Triangle ABC is definitely congruent to triangle AB prime C, because if ABC, if I reflect it, I get AB prime C prime. Notice that reflection, it's a rigid motion, therefore image and preimage are congruent. But now, this is what we're looking for now. What is the relationship between triangle AB prime C? In other words, this is the triangle that we're looking at. A, B prime, B. So what kind of triangle do we obtain when we perform this reflection? Well, this is 30, that's 30. That means the whole angle right here is 60. This is 60, and this is 60. So notice that the triangle that we have created by performing this reflection, we have created an equilateral triangle. Because all angles, our interior angles, are 60 degrees. But now, let's think back here for a second. Because now our next step is just write down the hypotenuse of triangle ABC in terms of A. So is it possible for me to come down, or for me to write down an expression? Well, let me actually highlight it here. I think it will be make a little more sense. So what we want to see is it possible for me to write down the hypotenuse of angle ABC? So this side right here. Is it possible for me to write down this line segment in terms of A? Well, let's think for a second here. I know that B and C should be half of B prime C prime because BC should be congruent to CB prime. So therefore, this whole line segment right here should be of a value or should be of a length of 2a because this is A, therefore B prime, that's 2a. But what do we know about the outer triangle? We just shown that it's an equilateral triangle. So therefore, this whole line segment is 2a. Then therefore, from A to B, it should also be equivalent to 2a. So what we have shown is that the hypotenuse of this right triangle, because recall that we started with this right triangle. So don't get overwhelmed with all this. Let's just think back on how everything started. We started with 60 degrees. We started with 30 degrees. We said that this was C. We said that this was A and this was B. All we have shown is that the hypotenuse, it's always going to be equivalent to twice the length of the shortest. And this is another expression to really keep in mind. So let's actually formalize it in words. So for D, what we have shown is that the hypotenuse, it's always equivalent to 2 times the shortest side. And how do I know that is the shortest side? Because that's 90, that's 60, that's 30. Notice that A is opposite of the shortest angle, which is 30. So A should always be the shortest side. So keep this in mind. Another way of seeing is that C is equivalent to 2A. Okay, so if we continue with our discussion, because now notice that, okay, so I know that the hypotenuse will always be twice as large as the smallest size. But can we write down an expression for B? Well, for that, we're going to use the Pythagorean theorem because I know that the Pythagorean theorem is applicable because we do have a right triangle. So I know that the Pythagorean theorem states the following. The Pythagorean theorem states that a squared plus b squared is equal to c squared. But notice that I already know that c is equivalent to 2a. So let's just substitute that. So now my Pythagorean theorem becomes the following. A squared plus b squared equals 2a squared. Well, let's simplify this because now this becomes a squared plus b squared equals 4a squared. And let's solve for b because now if we solve for b, let's take away an a squared here. That way this goes away. And now I have that b squared is equals to 3a squared. If I want to solve for b, I must take the square root. So therefore the square root cancels out. And now I know that b is equivalent to the square root of 3a squared. But we can definitely simplify this because now this becomes the square root of 3 times the square root of a squared. In this case, that will cancel out. So now I know that b is equivalent to square root of 3 times a. But let's just put this result in words, because what we have shown is the following. We have shown that b will always be equivalent to square root of 3 times the shortest side. And these are just ratios that we should always keep in mind. These are just ratios that we're going to be using throughout the rest of geometry because these are the ratios that we're going to encounter for those special right triangles. So let's just summarize this. Let's actually go back and write down our conclusions. So in a 45, 45, 90-degree angles, the hypotenuse will always be square root of 2 times the length of the triangle. So this is only true for a 45, 45, 90. And in any right triangle who is of 30, 60, 30, 60, 90, what we have shown is the following. What we have shown is that for any right triangle, let's call this 60, so let's just be formal, 30. If we let A to be the shortest side, I know that the hypotenuse will always be equivalent to 2 times the shortest, and I know that the second leg will always be equivalent to square root of 3 times the shortest. And notice that these are just ratios that we have to keep in mind, because these are just ratios that we can use to find sides in right triangles. Make sure that you do have these ratios somewhere on your notebook. But let's actually apply our conclusions. So here, notice that we want to find the value of x and y. But the first thing that you might have noticed is this. We cannot use the Pythagorean theorem right here. We can just not use the Pythagorean theorem because we only know one of the sides and we're looking for 2. So the Pythagorean theorem is not applicable here. But I noticed that this is one of those special right triangles that we have just discussed. And in addition, notice that I know the length of the shortest side, which is what we use as our A in our in the example that we were just discussing a couple seconds ago. So if we recall our conclusions, we definitely want to use the ratios that we just derived using a 30, 60, 90. And if I want to find the hypotenuse on a 30, 60, 90, we have already stated that the hypotenuse it's always twice the size of the shortest side, which in other words is 2 times A. So in this case, x is equivalent 2 times A. But notice that we know what A stands for. A is the shortest. So in this case, x is 2 times 6, which is just 12. So notice how important it is for us to have those ratios in our discussions. So now C represents the second leg, and we have said that the second leg will always be equivalent to square root of 3 times the shortest. So in this case, y is square root of 3 times A. So therefore, y is square root of 3 times A, where we know that A is 6. So y is the square root of 3 times 6. And just for formality, we always just put the number in front of the radical. So 6 square roots of 3. Okay, so notice that we were just not able to use the Pythagorean theorem, but if we recall those ratios that we just discovered a couple minutes ago, then we can definitely use those ratios to just find the length of the missing sides. All right, so let's do a couple more examples for you to see how we can use this information now. First thing to notice is we want to find x and y. We cannot use the Pythagorean theorem because we only know one side. So therefore, we can also notice that we have a 30, 60, 90 degree triangle. So therefore, we can use one of those ratios. So let's just label this as we would have just, let's just label this. So x will represent my A because that is the shortest side. And I know that the hypotenuse is 2 times A. And I know that the second side is 2 times the square root. Nope, typo here. The hypotenuse is square root of 3 times A. All right. So how can we go about this? Well, there's different ways to go about this, but the way that I'm going to encounter is just to use this idea because I know that A is going to be equivalent to the square root of 3 times a. So I can definitely find the value of a here. So now if we solve for a, we want to just find the square root of 3 to find the square root of 3. So now I know that a is equivalent to 8 times the square root of 3. Recall that we never want to have a square root in the denominator, so let's rationalize the denominator. So we can multiply with the square root of 3 on the top, square root of 3 on the bottom. So a is just equivalent to 8 square root of 3 over 3. Now let's just pause here for a second and let's just actually write down in words what we did here. So what we did here is to use the ratio that said that the longest side, or the longest leg, is always equivalent to the square root of 3 times the shortest, which is exactly what we're doing, what we were saying here. 8, it's equivalent to square root of 3 times a, but recall that a, it's always the shortest. So this is essentially what we just did here. Longest side, which is a, equals to square root of 3 times the shortest, which is a. So, but a represented x. So what we have said here is that x is equivalent to 8 square root of 3 over 3. So the only thing that we're missing here is the value of y, but notice that I already know what a stands for. So I'm going to be using the ratio that states that the hypotenuse is going to always be equivalent to square root of 3 times the shortest, which is essentially what we do have here. The hypotenuse, which is y, is going to be equivalent to 2 times 8. Oh, sorry. I see that I wrote down square root of 3 here, so that's a typo, because we said that that's equivalent to 2, not square root of 3. So there it is. So the hypotenuse is always equivalent to twice the amount of the shortest. So we know what the short is. The shortest, we just found it to be this weird expression here. So now I know that y is equivalent to 2 times 8 square root of 3 over 3. And finally, we can see that the way that we multiply this, we can put over 1. And numerators with numerators, denominators with denominators. So 2 times 8, that's 16. So we got 16 square root of 3 over 3. Okay. So I hope that this was helpful, and I'll be seeing you in the next lesson.